Thank you. And thanks to the organizers for what's been a great conference so far, and thanks for affording me the opportunity to speak. I'm not normally a Schubert calculus person. I'm normally a symmetric function person, which is why my talk will have Schur functions featuring probably more prominently than Schubert polynomials, but all the motivation for everything that I'll say really comes from the Schubert setting. So I'll try to keep that in. So like many people, I'm not actually going to rigorously define a Schubert polynomial, but my excuse is that I don't normally work with them. So I'll just give you sort of a loose definition. So, and let me know if my font gets too small, please. So the Schubert polynomial, which I'll use this notation, is, well, it's a polynomial. And I like infinitely many variables. So it's a polynomial representation for the Schubert classes in the cohomology of the flag manifold, as I guess we've been seeing all week. So just to steal a definition, and sorry if I get any attributions wrong, but I believe this definition, which is one of my favorite definitions, is actually due to Lescaut, which is that this is the unique homogeneous polynomial of the correct degree. And the correct degree, of course, being the Coxeter length of W, that represents the Schubert cycle of W. So that's a perfectly reasonable definition, although possibly it'd be hard to write down a polynomial from that. So these guys form an additive basis, right, for the ring of all polynomials. So one fun thing to do is to take another polynomial. I don't know, just for kicks, we can take this one. So take some random polynomial and you want to expand it in terms of Schubert's. So this is sort of a fundamental problem in Schubert calculus is taking these two guys and now expanding it out. And we'll do it again. So S infinity, I just mean it's all the permutations that fix almost every point. So C, U, V, W, sigma, W. So one of the goals of Schubert calculus, as I understand it, is to really understand these coefficients. So as Dave explained to us on Monday, I think, we know these are non-negative because of the geometry. So what are they? So C, U, V, W enumerates flags in a suitable triple intersection of Schubert varieties. So from that, we know that they're non-negative. So being a combinatorialist, I want to have some nice combinatorial thing that they count. So that's the fundamental problem for me. So let's see how it goes. So find a positive, cancellation-free, manifestly positive, combinatorial, let's say construction for C, U, V, W. So I guess according to Under's book, we should also know that it's P sharp to compute them. But for me, I'm just happy if we have a positive combinatorial formula or construction. So sort of the idea is that what should an answer look like? So what kind of answer am I looking for? So this is sort of what I'm looking for. So possibly these numbers, C, U, V, W, count, say, saturated. I think in Mark Shimozono's talk, he was talking about chains in Bruja order, and saturated just means you don't skip steps. So that's what I mean here. So possibly saturated chains in Bruja order. And if you're not sure what Brouillard order is, it's over there. I'll explain it. Saturated chains in Brouillard order from U to W with some condition imposed by V. Now, is that vague? Yes. If I could say it specifically, I would be done. So, but this is sort of the flavor of the answer that I'm looking for. So, I want to know that these numbers count saturated chains in Brouillard order, which is the ordering of permutations, starting at U, going up to W, and you only take certain chains that satisfy some condition that V is telling you to do. Okay, that's sort of the idea. So let me give you an example of where we actually know the answer. And I should say, Brouillard order here is the same as inclusion of Schubert varieties, so it's really the natural order to use in this setting. So here's a special case that I can do, and I'm sure you can all do it too. So the special case is the Littlewood-Richardson rule. So what is this? Well, now we get to my friends, the Schur functions. So they're not telling me anything. So here, lambda is a partition. So these guys form an orthonormal basis for symmetric functions. So the ring of symmetric functions are sort of the best basis for it. And I can tell you just to define them, and I'll just stick with my idea of defining things sort of loosely, although maybe this is a little more concrete. So this is the character of the irreducible representation of GLK indexed by lambda. So if you take the irreducible representations and you take their traces, then these are giving you the Schur functions. And when I say the orthonormal basis, I'm thinking of a Hall inner product, which is the same as the inner product that you get on characters. But I guess since we want to talk about geometry instead of representation theory, that's all I'll say on the GL in front. So again, they're an additive basis for the ring of all symmetric functions. So we can do things like expand other symmetric functions in terms of the Schur functions. So a nice one to expand would be take S lambda, multiply it by S mu, and now it's a basis, so that's going to be a symmetric function, so I can write it as the sum over all partitions nu of C lambda mu nu S nu. And I want to know what those are. So I use the same letter C because they really are completely analogous here, right there, some of them. So C lambda, the Littlewood-Richardson rule tells us explicitly what these are. So these are the number of saturated chains in Young's lattice, which is a suborder of Brouillard order, and there's Young's lattice, and I'll explain more about that in a minute. So there's saturated chains in Young's lattice from lambda to nu that happen to have something called, there's a statistic you can fill in this weight, which gives you a partition back, and the weight that I want is the weight mu. So I take certain chains in Young's lattice, and that gives me these. So from the theorem, the Littlewood-Richardson rule that tells me what these are, I know they're positive, and this has the right flavor that I was looking for. So I called it a special case, and it looks like I've just made an analogous thing and just switched over to the playground I wanted to play in, but I'll tell you why it's actually really the same area. Right, so why is this a special case? So let's talk for a second about Gauss-London permutations. And I'll tell you what these are. So the Gauss-London permutations, they're going to take input lambda, which is going to be a partition, and it needs to fit inside, and they're also going to have an integer k, and lambda has to fit inside a certain rectangle, which is a k by n minus k rectangle. And here k is going to be a number, or let's see, yeah. So it's going to be, let's see, the Gauss-London permutation associated with lambda and k is going to be the unique permutation of shape lambda that has a single descent and it happens at position k. Okay, so the formula explicitly for that would be the permutation v of lambda k is going to be the permutation that sends I to, and I always script indexing, so I'm going to copy this one down hopefully correctly. So this is the map, and now just before I give you the example, let me just motivate it. Here's the result, that if you take a Schur function, S lambda, and you evaluate it just at the first k variables, then this is actually honestly equal to a Schubert polynomial, and it's equal to the Schubert polynomial. So when I tell you this is a special case, it's not just that it's completely analogous, these really are Schubert polynomials. So I do know something about Schubert polynomials. So here, let me give you this motivation. Here I've done the map a little bit. This is Young's lattice, so it's a lattice on partitions. The covering relations are add a box. And so you go up this way. I've left off some partitions here. And it's because they're going to die under this map. And I really want to illustrate this map. Here I picked k to be 2 so that I can do an example that fit on this board. And these are infinite permutations. So when you see dot, dot, dot at the end, that just means put the numbers in increasing order, all the numbers that you have left. So this is the permutation that sends 1 to 1, 2 to 6, 3 goes to 2, 4 goes to 3, and then the next one goes to 4, 5, 6, oh sorry, 5, 7, 8, 9, and so on. So you keep the rest of the numbers in order. So if you get bored and want to find exercise, you can make sure that I didn't make a mistake and let me know when I did. Right, so the Littlewood-Richardson rule is actually a special case of the formula arrays that we care about, and the case that I actually really want to do for this talk is on the board here, and it's the case where we take a Schubert polynomial, arbitrary Schubert polynomial, multiply it by a Schur function, so a Grassmannian Schubert polynomial, and expand it back in terms of Schubert polynomials. So these are the coefficients that we're getting. They're not all of them, they're only the ones where this entry is actually a Grassmannian permutation. So it's sort of the next step up from the Littlewood-Richardson case is I'm letting one of these things, instead of being a Schur function, be a generic Schubert polynomial, and now the expansion has to be back in terms of Schuberts. So let me tell you how all the rest of the talk is going to go, or at least how our approach to this problem went. So, right. So my collaborators, Nantel Bergeron and Frank Sotilli, have a paper from 1998, I believe, where they worked on this problem and this specific case. So I'll say Bergeron and Sotilli translate the problem to finding the Schur expansion of a particular quasi-symmetric function. And I will define quasi-symmetric functions. So they basically translated the problems and they say, well, if you want to know what these coefficients are, then all you have to do is take this quasi-symmetric function that I'll give you and figure out what its Schur expansion is. So that's a classic problem to get in symmetric functions. You're given a function, you hope it's symmetric. If it is, you want to find its Schur coefficients. So they have a specific thing there. So my contribution on this was I use something called dual equivalence to find Schur expansions. So in my thesis and beyond, I sort of use this machinery called dual equivalence, and I use it so that if you give me a quasi-symmetric function, I try to use it to find the Schur expansion. And so then I guess we'll attribute the next step to Banff, although specifically it needs to be attributed to Valera, Billy, and Stanley. They had a workshop on quasi-symmetric functions, which are really awesome, and that's one of the main things in my talk. Quasi-symmetric functions. And they invited all three of us. And then we talked, and then we discovered that if we add the bits that we have together, then we got a nice theorem out of it. So really the first half of my talk is the introduction setting this up. The second half of my talk will be explaining to you what Bergeron and Sotilli did and the function, the quasi-symmetric function that they defined. And then the third half will be explaining dual equivalence and how you use that to get a quasi-symmetric function. And then we'll have an answer to what these guys are. So, questions so far? Page 2. Okay, so, right. So if you happen to have read this paper from 1998, then various run instantaneously define something that they're going to call a K-Bruja order, and I'm not going to call it that. So I'll just put an equivalence here. K-Bruja order is the same thing as Grassmannian Bruja order, which is the new name for this, and it's Frank approved. So apparently it's not good to have a parameter in your title of your order, so we're going to call it this. So Bruja order, as I mentioned, there's an example on this board. So it's the classic order that we're going to study. And we're going to look at sort of variant of that. And the variant is going to tell us how to pick out certain saturated chains. Basically what the Grassmannian Bruja order does is it takes regular Bruja order and then it forgets about some of the chains. Okay? That's how we're going to kind of get a subset depending on the extra parameter. So first, what's Bruja order? So Bruja order on S infinity as covers, it'll tell you what the covering relations are, and the covering relations are drawn in there. So U is covered by W if, well, first of all, the length has to go up by 1. Possibly you're not programming this. Plus 1. And W has to be U times the transposition. Okay, so you multiply by transposition and you go up. That's what Bruja order is. Young's lattice, as I said, is add a box. So the size goes up by 1 and you have containment. So what do we know about Bruja order? Well, the easiest thing you know about this, if you're me, is Monk's rule, which you might not remember the name for. Monk's rule is like the degenerate Pieri rule, or rather the easiest Pieri rule. So it's the case where I want to go up, but as little as possible. So Monk's rule, I'm going to multiply by a box, a single box. And in this case, if lambda is a single box, my Grassmannian permutation is pretty easy. It's just going to be the transposition that interchanges k and k plus 1. So, and you can just figure that out from the definition, which might still be on the board. So it's just going to be the transposition k and k plus 1. So what I'm going to do is I'm going to take my Schubert polynomial, and I'm going to multiply by the Schur function that I know, but the Schur function for a single box is actually pretty easy. It's the same thing as many other functions, A's, H's, and all that. All right, so this is my Schur function, and now I'm going to expand it out, and Monk's rule tells me what this expansion is. It says, well, you sum over all numbers A and B that straddle K in this way, but you also have to have the condition that the length of U times AB is equal to the length of U plus 1. Right, that's no surprise looking at the thing in Bruja order. And then you have, okay, the Schubert polynomial. So here, you think of this as you're summing over all ways to go up by a transposition, but that transposition is somewhat special. It has to straddle the number k. Okay, so this is Monk's rule. It gives us a beautiful answer to this problem in the case where lambda is a single box. So inspired by this, we're going to have the Grassmannian Bruja order. And it's going to have covers. So its covering relations are going to be basically everything that appears in Monk's rule. So you're going to say that U is K covered by W, the little K down there, if, so the length of W has to equal the length of U plus 1, that hasn't changed. And you want W to equal U times the transposition, that hasn't changed. And you now have an addendum, which is that A and B have to straddle K. So this condition here means that I've just dropped some of those covering relations in Bruja order. So I'm only selecting certain chains now. If I've got chains in this Grassmannian Bruja order, it's a subset of the chains in the regular Bruja order. So I now have a new order, and I want to talk about chains in it. So when I say a chain, I mean a saturated chain. I guess a Grassmannian Bruja interval, which is going to be denoted UW with a little k here, depending on what k is. It's going to be a chain, so it's going to be start at U, and that's going to be x1, And then you're going to go up A1, B1 to X2, and A2, B2. Let's see. AN, BN, let's say you go up in steps. Let's take it XN plus 1, and this guy had better be W. So this is what a chain is. All right, let's go one step at a time, each time, and go all the way up from U to W, so suppose there are n steps in there. Now, those of you who know about quasi-symmetric functions and know about my preferences, I like to index them by descents, so I want to tell you what a descent set. So it's just a statistic associated to a saturated chain. It's pretty easy. It's actually the descents that, similar to the descents that you get for words. So the descent set of the saturated chain C is just going to be the set of those I where BI is bigger than BI plus 1. And here, by B, I mean that second thing in the transposition. Okay, so A is the smaller one, so you just look at the word you get from those bigger, from the rightmost numbers, and then you take descents in the usual sense. So the theorem, the first theorem, which is from Bergeron and Satilli in 1998, is that, let's see, so G, my new function, of UW is going to be indexed by an interval in this order, this Grassmannian-Gruha order. The first half of the definition is a theorem. The first half of the theorem is a definition. It's going to be the sum over all saturated chains in that interval of the quasi-symmetric function, which I have yet to define, and I will define it shortly. So hang in there. So far it's just something with a Q. So the quasi-symmetric functions indexed by this. So that's the definition, and now the theorem part of the theorem is that this is equal to the sum over all permutations, all partitions of C, U, V of lambda K, W, S lambda. So when I say that they translated the problem into one of symmetric functions, this is what I mean. So they define this quasi-symmetric function, and the theorem that they were able to prove is that in fact it's symmetric, and its coefficients, when you expand it in terms of Schur functions, are the coefficients that we're really interested in. Okay? So, to me, what this theorem says is that if you want to study Schubert calculus, and this particular problem in it, then you could just study symmetric functions, and this particular problem in it. I'm looking at this function. So now let me decrypt this a little bit by telling you what a quasi-symmetric function is. So, I'm assuming everybody knows what a symmetric function is if you haven't seen it before just from the name. But a quasi-symmetric function is sort of, it's a superset of symmetric functions, and it's sort of the shift invariant is what I like to think of them as. So we have QSym, and it contains the symmetric functions. And I'll tell you, let's see. So Gessel gave a basis for this. And so I'll call it the fundamental basis or Gessel's basis. And quasi-symmetric functions are a vector space, and their dimension is 2 to the n minus 1, so they can be indexed, or 2 to the n, so they can be indexed by subsets. So if you take a subset D, so let's just say D is a subset of n minus 1, then what's Q sub D? Well, you sum over all n tuples, so I1 less than or equal to in, and you're going to multiply those polynomials or those guys together. And now where the D comes in is it's saying you have to jump. These inequalities have to be stripped whenever you hit this descent set. So it says that if you have a descent, that implies that you have a jump. Okay, so for example, Q13 is equal to x1. So because 1's in there, the next one has to be bigger. So it could be x2. But the 2's not in there, so those could be the same. And then you have to jump again, x3. Plus x1, x3 squared, x4, say. And basically, I can keep the exponent 1, 2, 1 and just keep shifting my numbers up. So that there are any numbers that just get bigger as you go. Plus, now I doubled up my middle variable, but I didn't have to. So there's plus more stuff, plus x1, x2, x3, x4. And again, if you want more variables, you can just shift out. And so x1, x12, x108, x1,019, for example, would be a term. So maybe that'll be another plus. So you sort of think of them as shift invariant. You keep the exponents the same, and you just sort of slide along your subscripts, as long as they get increasing. So that's the quasi-symmetric functions. They're fundamental for many reasons. And let me tell you one of the things I like about them. So standard Young tableau, let's go to this board. So a standard Young tableau is a saturated chain in Young's lattice. And normally the way you see them written is, as you add a box, you put the next number in that box, and then it'll turn out that your numbers, because you're going up in that order, your numbers are going to be increasing along rows and columns. But you can think of standard Young tableau as just saturated chains in Young's lattice. And it's good to think of them that way. And I'm going to throw a statistic at them. So the descent set is, if you read them the way you would read a book if you're using French notation, but actually kind of works with most reading orders. But using French notation, it's going to be the times where you have the box for I plus 1 is above the box for I. So whenever you add a box up, you just created a descent. Okay? So when you're doing here, as long as you stay in the rows, you've got no descents, but as soon as you go over this way, you've just created a descent. So that's a statistic, and it's similar to what we had there. And the theorem, the reason why quasi-symmetric functions are really going to help us solve this problem is not just because they appear here, but because they relate nicely to Schur functions. So beautiful theorem of Gessel's, 1984, is that if you sum up all of the tableau of a given shape, and you throw in the fundamental quasi-symmetric function, indexed by the descent set of that tableau, and you do it for all the guys with the same shape, you get a Schur function. So that's a very powerful result. Even though it's, once you write it down, it's not very hard to prove, but it turns out to be a very powerful way to think of things. So the idea here is that, okay, we've got some sum of quasi-symmetric functions. We want to know what the Schur coefficients are. Well, what you need to do is group the quasi-symmetric functions together into Schur functions, right? And then just count how many clumps of Schur functions you have after that. And what Gessel's telling us to do is how to do that. If you somehow get these objects to look like tableau, then you just group them together according to shape, and now you've got your Schur functions popping out. And so that's the idea of the third half of my talk, which starts now, which has to do with dual equivalence. So, Heyman defined dual equivalence. And I should say that in Alex Jones' talk, he talked a lot about jeu de Tacan, and that's a powerful tool that we all know and love. Dual equivalence is called dual because it's dual to jeu de Tacan. So if you're doing, say, the RSK algorithm, then the left tableau has jeu de Tacan, and the right tableau is dual equivalence. It's possible I have left and right backwards, but I think I did it right. Pretty sure. The Q tableau has to do with dual equivalence. I know that part's right. So he defined dual equivalence involutions, which I'll call D sub I. Here, I is a number strictly between 1 and n. That swap I and I plus or minus 1, whichever one's further away. And what do I mean by further away? Well, in the reading word, one that's like farther away. So if you see, for example, 2, 1, 3, then you switch 2 and 3. A better way to think of it is that because Young's lattice is super nice, every rank 2 interval is going to be Boolean, so it either looks like this, or it looks like this. I'm sorry, this one died. Okay, and so what Heyman's dual equivalence says is that you look at the right spot, the right rank, based on I, and then you just switch this path for that path. So for example, if I was going to do a dual equivalence on this guy, like this saturated chain would become this saturated chain. You sort of just switch which way you go on that diamond. So that's a nice thing. And the theorem, which I'll put in here. So the theorem of Heyman's from 1992 is that I can basically do a paradigm shift. So his theorem says that the dual equivalence class of a tableau, so if you take T to be a standard in tableau of shape lambda, then the theorem is that its dual equivalence class is all the tableau of shape lambda. So it's the whole set. So now what I can do is change Gessel's theorem in a really trivial way. I'm erasing standard young tableau, and I'm putting the dual equivalence class of my favorite tableau of shape lambda. And I do have a favorite, and if I have time, I'll tell you what it is. But the idea here is you put in your, instead of thinking of this as a set of tableau, you think of it as all the tableau in an equivalence class, or all the objects in some equivalence class. So that's going to help us solve this problem. Questions? Okay. So how do we solve this problem? Well, the idea is that now that we're not talking about tableau or saturated chains or anything like that anymore, we're just talking about objects with an equivalence relation on them and how to group them together. And these equivalence relations, well, they happen to come in flavors of I, right? So it's DI, so there are different flavors of them. So there's a lot of structure on that equivalence class that you're seeing there. So here's a definition without too many details. So just in terms of a general tool, so given any framework where you have a descent map from some set of objects, here 2 to the n minus 1 just means I'm taking subsets of 1 up to n minus 1. So given any framework like that, which we have, a family of involutions, let's say phi I, and again, 1 is less than I is less than n. And the 1 is less than I is less than n just because you need to have I minus 1 and I plus 1, so you don't want to hit the endpoints. Is a strong.
What is the source of the map descent?
I'm sorry?
What is the source? Domain of the map descent? A? What is it?
Of phi. So phi is an involution on A. Sorry, so phi I goes from A to itself.
And what is, so I don't understand that one.
What is A?
A is some set of combinatorial objects. Some set of stuff.
Okay, thank you.
For example, it could be saturated chains in the Grassmanni-Bruchal order.
For example.
Or tableau. So A is just some set, and you have a descent map on that set. You have a descent statistic on that set. And then phi is an involution on A, and it's going to be called a dual equivalence. It's a strong dual equivalence. Sort of with Hayman's dual equivalence in the tableau in mind, if, and now is where the definition gets a little thing. So there's some conditions. Maybe I'll fill in a few of these. So it's got nice mixed points. Better explicitly described. The descents sort of toggle nicely. It's one of them. Sort of, if I was a descent and it's not anymore, or, yeah. The descent sets toggle nicely when you apply this map phi. It changes the descent set in a nice way. That's made rigorous elsewhere, but equality is, well, sometimes phi I is equal to phi I plus 1, and we know exactly when that happens. There's a commutativity, and this, so maybe I'll put here, sometimes phi I equals phi I plus 1. Commutativity says that phi I composed with phi j is equal to phi j composed with phi I whenever I and j are far apart. And the definition of far apart is at least 3. And then there's this minimality one. Minimality. And this one's all. It's not local. So there's some axioms. These first 4 axioms are really local. Local in the sense that you can check them like locally. This last one's not. You sort of have to check it on the entire set of things you're looking at. It's really hard to check. It's definitely a pain. But there's a payoff if you check it. So the payoff is that this definition of dual equivalence in general captures the spirit of what Heyman did on Tableau in the following sense. So here's a theorem. If Pi is a strong, now I put this in parentheses because I don't think this word appears in any of the papers, but it will soon. It does on my computer, maybe not on the archive. Strong dual equivalence for, right, your set A and your map does, right? So your set and your statistic on the set. So if you have a strong dual equivalence, then if you sum over everything in your set of Q to the des of T, then it breaks apart really nicely in terms of Schur functions. A lambda, S lambda, where this guy is going to be explicit positive. Or rather not negative. But the idea is that it captures it in the sense that the phi's, if you look at the equivalence class under the action of the phi's, they group together into Schur functions. So this is just counting, this basically enumerates equivalence classes in a really nice way. So A lambda will just be the number of equivalence classes where the Schur function that you end up grouping is lambda. So in particular, if we could do this, if we could set up this framework and apply it to the Bergeron-Santilli quasi-symmetric function, then we would know what these coefficients are. Unfortunately, you only ever call something strong if there's like a weak version, right? So let me say there's another theorem, which is that if Phi is a weak dual equivalence, so that means that you get to, you skip the minimality, you skip the awful condition. So I'll just say drop 5, and you weaken 3. If it's weak dual equivalence and comes from words, and I'll say a little bit more about what I mean by that in a second, it comes from words, then you get Schur positivity, and you get an explicit thing, but it's not as explicit. So this is actually equivalence classes. So I'll say then you get Schur positivity, but A lambda is complicated. What do I mean by that? Well, what I mean is, if you have a strong dual equivalence, the things break up into nice, neat little equivalence classes, each one corresponding to a Schur function. If you have the weak version, then some of these guys morph together, and instead of getting a single Schur function in equivalence graph, you get something that's Schur positive, but it could have lots of Schur functions in it. So they sort of group together badly. But
what was your favorite to roll in the class? Do you have your favorite
so,
representative of your class?
what a well-timed question, thank you, Arun. So here we have a favorite representative, and he's easy to pick out, and he tells us what lambda is. So if you have your equivalence class, right, then all I have to do is say, oh, I know what my favorite guy looks like in this class, just based on the descent set. I know what my favorite guy is. So I'll find him, and then he'll tell me what lambda is. And I just have to count my favorite guys that appear, and then I can take all their lambdas, and it's super easy. In this class, it doesn't work so well, because now there are multiple favorites, and there's some guys who think they're favorite, but they're not really. So you can't pick them out so easily. So that's exactly what breaks down here, is your favorite guy doesn't save you down here.
Just like in real life romance.
Because there are multiple favorites in the class. All right, so that's sort of all said in some kind of general framework. So I guess I have a fourth half of my talk, but it's really short. So the last half is that we have a monoid structure for the Grassmanni and Bruja order. And that leads us to a 6-case involution on chains. So basically, you're going to look at these guys. You want to do one of these dual equivalence moves, and there are basically 6 cases you have to follow. And interestingly enough, those 6 cases are in unpublished work of Bergeron and Satilli from when they were working back in 1998 on their result. They didn't publish it because, actually I'm not really sure why I like the result, but they didn't publish it, but they had these involutions written down. They didn't think of them as involutions, and they didn't think of them at all the way that I did, but when we were all talking together, I was sort of, well, we're going to have to think of these maps, and then Tel's like, well, you know, we did some stuff with some maps. We have these, and I'm like, that's it. That's all you need. So they actually had everything that they needed. They just weren't thinking of it in the same way that that I was thinking of it later. So they actually had those maps, and the theorem is that the maps work. So these involutions that we get give, and it's sad, but it is weak. It's sad but expected that we get a weak dual equivalence. For, and the set is the set of these chains. Des is the descent map that I told you about. And that implies that we get a combinatorial proof that C, U, V, lambda, K, W, that they're non-negative, and we do have a formula, but you know, before I think Anders Buch had said, oh, we should be able to see that things are p-sharp. Well, you actually can't see much from this formula. It's really kind of a nasty, ugly formula for these guys, but it is a formula nonetheless. But another nice thing that we get is that sometimes we have a really nice formula. So I'll say if W U inverse avoids 6 specific patterns of some of them are linked 6 and 2 of them are linked 7. So pattern avoidance in the usual sense of pattern avoidance. So if we avoid 6 certain patterns, this is a strong dual equivalence. And that implies that we actually get a nice formula in that particular case. So I guess I'll say one more thing is that when Bergeron and Satilli were working on this, one thing, sort of the way they had come about these involutions that they already had, that they weren't thinking of as involutions, they were trying to do a Schur type move on these chains. And much in the same way that Alex was motivating the power of Schur and giving you these nice formulas, that's exactly what Frank and Natel were trying to do. They weren't quite able to do it in a lot of cases, and it was really frustrating. And it turns out that those cases where you couldn't do it are exactly where you're going to get the weak instead of the strong dual equivalence. So somehow this idea makes it a little easier to capture things that aren't so well behaved that a natural Schur is popping up. So when the natural Schur pops up is exactly when the better version of dual equivalence holds, but we can still handle the bad cases that they weren't able to handle before. We just have to use the weaker version, and we have to settle for the fact that we don't get a nice formula that says, pick out my favorites, it tells me everything. The formula gets a little more complicated. So I think that was all I wanted to say, so thank you very much for your attention.
Question?